Alrighty, let's do a couple of practice problems with parametrics in polar form. And these are, I call them parametrics in polar form because the independent variable is theta. And they actually want an arc length here, the length of one arch of the cycloid with these parametric equations. So we go to parametric arc length, which is the integral of the square root of dx dt squared plus dy dt squared. And then we have a d theta out here instead of a dt like we did in our last lesson on day one. So we need to find dx d theta. I'm not sure if I said dx dt or dx d theta. I meant dx d theta squared and dx dy d theta squared, excuse me. We're in theta here. So if I get dx d theta, I'm going to have 1 minus sine goes to cosine. So 1 minus cosine theta, that comes over here. And remember, I'm squaring it. And then dy d theta is just going to be sine theta because 1 goes to 0 and negative cosine goes to positive sine. So that means a sine theta in here. As you might imagine, this is going to be a calculator problem. We're not going to mess with working this all out and trying to simplify it by hand. And so what we want to do, though, is figure out our limits of integration. And part of it is knowing what an arch of a cycloid is. And you could pull this up on your calculator, graph it, and see how long it took you to get all in all around the whole cycloid. In fact, I'm going to recommend that you do that just so you can see it. And what you're going to do on your TI-89 is you're going to go to mode, and then I believe it's page 2. No, it's page 1. It's the very first item that you're usually in function mode. You're going to switch to polar mode, and you're going to actually don't do it on polar mode because you don't have R's. Do it on parametric mode. So go in here and do this on parametric mode, and then instead of typing in thetas, you'll type in t's as your independent variables. But it'll give you an idea. If you type in this x and this y, it'll give you an idea of what this graph looks like. It doesn't really matter what it looks like, and you're never going to be expected to graph these. They're probably going to give you the graph, and then you can tell what's going on. But in this case, the one arch takes us from 0 to 2 pi, which is fairly standard in polars, that one loop around the unit circle is 0 to 2 pi. Those are going to be our limits of integration here. And so when you put this all into your calculator, you're going to get a very nice arc length of 8. So let's go to a multiple choice problem. This one is talking about a hypocycloid. Again, they didn't give you a graph. You don't know what this looks like. This is not a calculator problem because you're just picking the equation or the setup because they want you to find area. Now, that's going to take us trying to figure out some things since we don't know what a hypocycloid looks like. We assume that it's going to take us from 0 to 2 pi to get all the way around the unit circle. But if you notice here, we don't necessarily have 0 to 2 pi, so we have to figure out what's going on. So what we want to do is we know area is the integral of y times dx. So we have our y value here. We have the integral of sine cubed t, and then dx is the derivative of x. We'll just do dx dt. We need a chain rule, 3 times cosine squared times negative sine. So that means our dx is going to be, let's see, I'll call it negative 3 cosine squared t sine t, and then of course we need a dt out here. So I'm going to work to clean up what I have. I don't have limits of integration yet, but I kind of want to simplify what I have. I'm going to pull out a negative 3 out in front of the integral sign, and I'm up to the point where I need a sine to the 4th and a cosine squared. And the nice thing is that eliminates b and c, which don't have the correct integrand. I have two situations that both have sine to the 4th times cosine squared. So now the real trick is, what are our limits of integration? And our choices are basically 0 to pi over 2, pi over 2 to 0, or 0 to pi over 2. So it looks like they're going in fourths here. So I'm thinking that a hypocycloid is going to have to go from 0 to 2 pi, which is pretty standard for a polar. Doesn't always take 0 to 2 pi, but the standard period would be 0 to 2 pi. And they've broken me up into either pi over 2 to 0 or 0 to pi over 2. So that's only one quadrant. So I'm going to just make a leap of faith here that I need all 4 quadrants. So I really need to multiply this by 4. So my guess is going to be D here. because of the fact that I only have one quadrant of my limits of integration, but I really needed four quadrants, so I'm going to have to take this 3 and multiply by 4. Now, I do see the sign issue, and I'm going to tell you right now that you're probably going to have to be given a graph to do this one, or you're going to have to be given more information. This is what this hypocycloid looks like, and you'll see that one quadrant means I integrated from 0 to 1 in terms of x values. And so we really need to switch those in terms of t. And so when I plug in to this to get out t, if my x value is 0, that means cosine has to be 0, and that happens at pi over 2. And then if my x is 1, then cosine has to equal 1, and that happens at 0. So my limits of integration are actually pi over 2 to 0. And then I have to multiply by 4 to get more than just one quadrant, to get all 4. And then the reason why we get to d is that we took our negative here and we flipped our limits of integration, which negated the integral and made it a positive. So we have a positive 12 and the limits from 0 to pi over 2.